All right, so a quick summary from last time. We were talking about surface integrals, and remember the big idea of a surface integral is that, like every other kind of integral we define in this class, we've got some quantity where the whole is the sum of the parts. Chop it up, add it up, however you want to say it, right? So, well, if you do that on a surface, then you end up with something called a surface integral. And again, we talked through the details and etc. I'm just hitting highlights here as a summary for the moment. Okay, we also realized that surface can be viewed as an image. That's what parameterization is, after all. And viewing a domain as an image allows for doing pullbacks. Think change of variables, right? I mean, technically is a little bit different because the dimensions are different, but it's morally equivalent to change of variables. And we worked out a specific computational formula. Okay, so we saw some examples, various quantities, different physical quantities that can be computed with this. And then we tried to apply the idea, same concept, to flux. Reminder from chapter 3 that flux involves, it's this formula, and it's, we motivated it thinking about the point of view of a vector field representing the flow of a fluid, but of course this as a quantity exists independent of how you're thinking about it. It's just a definition. Okay, so what we found though is that things go a little different. Importantly different and unavoidably different. After all, if you're going to be defining flux based on, among other things, this dot product, right, then it depends, in the sense of a minus sign, it depends which of the two perpendicular unit vectors to the surface you choose. Right? Depending on which one of those two normal vectors you pick, you're going to get different answers. Said differently, you have to choose, as part of the question, as part of what it is you are trying to compute a flux through, there has to be a chosen orientation, a chosen, collection of unit normal vectors defining which is the positive direction through the surface. In other words, your domain has to be not just a surface, but an oriented surface. We did not see this with scalar surface integrals. If you're computing mass, whatever, right? There is no such thing as direction. You're talking about mass or various other things. Okay, so with this in mind, we ended up with a new kind of integral. We call this a vector surface integral. Cosmetically, you can see that because the differential is a vector, the integrand is a vector. And computationally, again, a lot of our tools are already there. We've already talked about parameterizing and pulling back, and all the objects needed to play that game are already thought through. And we get this formula with which we did an example last time. And this is where we ended it. Okay. No, this is not where we ended it. Sorry. We got a little bit further than this. Okay. So I asked the question, does the parameterization matter? And in a lot of ways, no. But there is one critical way in which the parameterization does matter. And it's a lot like the story with vector line integrals. Namely, which direction you go matters, right? And so when you parameterize, you have to make sure that for line integrals, you have to parameterize in the same direction that your curve is going. And analogously here, you have to parameterize in such a way that your parameterized normal is consistent with the given surface orientation unit normal. You got to make sure, in other words, that you don't accidentally parameterize it upside down, parameterize it backwards, however you want to say it. Okay. All right. So I talked through where this messes up our algebra, and let me go ahead and zoom in a little bit more now. You can see a little bit better. We talked through where this messes up our algebra. I had made this claim that this is always equal to that because, after all, the capital N is a unit vector times a magnitude. The problem is that this one comes from the given orientation for our oriented surface, but this one, the one that is the direction of the parameterized normal, does not. It comes from the arbitrary parameterization that you've chosen. So this was the little math crime I committed. I conflated these two different unit normal vectors, it's an easy mistake to make. Again, I did it on purpose, right? But it's an easy mistake I made this mistake on purpose so that you could see how easy a mistake it is to make, and so that you will be heads up in the future going forward as to, well, wait a minute, what exactly do we have here? Okay, now, to the particulars. How do you decide? How do you realize whether you've parameterized it upside down? And if you have parameterized it upside down, what do you do about that? Do you have to re-parameterize, start all over? Conveniently, you don't have to start all over. Just if you've parameterized it upside down, realize that means every term in your integral is off by a factor of -1, which means your answer is off by a factor of -1. And just fix it by putting an extra -1 factor in there in recognition of where this mistake is made. Let's see that in action now. Here's an example. Okay, so now this example is going to look very familiar. Computing the flux. This vector field, same exact vector field that we looked at in the previous example. Same surface. The portion of that paraboloid sitting above the unit square. Everything's the same, with one little detail missing. I'm going to swoop aside for just a moment. We'll get to that detail in just a second. But other than that, it looks like the exact same example. And so here's the thing. With this equation describing the surface, it's a graph, so we use the graph parameterization. Of course we do. It's the easiest parameterization. Why wouldn't we? Right? We take various partials, no problem. We take the cross product of these per the formula, and we end up with this as our parameterized normal vector. Now here is where you have to heads up. We were told in the statement of the question, you can see it right here, we want the flux downward. Now this is arguably just lingo, right? But when the question says we want to compute the flux downward through a surface, what that means is that this is an oriented surface, and the orientation on this surface is between the two options of how you could parameterize it, the one that points downward, not the one that points upward, right? So this is a statement about the orientation of the given surface. When we parameterized, without even realizing it, there was also an associated orientation. Hard to tell by looking at the parameterization itself. Which way is this oriented, up or down? Okay, really hard to tell by looking. But when you get to this stage where you have your capital N normal vector, now you can really see whether this is upward or downward. And specifically, I've got a positive z component. This normal vector is upward. It was supposed to be downward. We got it wrong. Everybody see what happened there? Questions, feel free. So, whose fault is this? I don't know if I can blame. I'm going to point out, though, it's really not a problem, given that we have recognized that we parameterized it backwards. I guess technically it's my fault for parameterizing it wrong, but I don't really feel bad about that because A, it's impossible to tell as you're writing it down, and B, you don't need to worry. It's not a problem anyway as long as you fix it later. So don't worry about it at this stage where you're doing the parameterization. Just parameterize whatever seems like the easiest way. Just make sure to remember to check it once you've got your capital N vector identified. Check and see, and if you got it wrong, as we did here, right? We did not parameterize the correct direction. All we have to do to fix it is just say, oops, haha, I parameterized backwards, stick in a minus sign, and proceed. And don't even worry about it. That makes sense? It's just a minus sign. It's the only difference that an orientation makes. So put it in, and off you go. Questions? Okay. All right, now there's a couple of little, well, let's see here. How many sticky wickets am I going to talk about here? I'm just going to talk about one big one, I suppose. One thing that does really matter is where you stick in this minus sign. That really does matter. The point to keep in mind as I'm going through this point is that it's not about the answer at the end, it's about the reasoning, right? This is a class about reasoning. It's not about answers. We already know the answers. This is a class about making sure that y'all know how to make proper mathematical reasoning with the mathematical concepts and tools that are taught in this course. So part of making valid mathematical reasoning is that you don't write stuff down that's false, right? That's a big thing for mathematicians. And here's the thing, this right here and this right here are not equal to each other, right? The ds vector has an orientation that comes from the given oriented surface. Capital N does not. Capital N has an orientation that comes from the arbitrary parameterization you've chosen, right? So very importantly, these are not the same thing. So you have to have this minus sign here. You have to. If it's not there, then it's wrong. It's just wrong. They're just not the same, right? It is not rare for students to write down as follows, to say, okay, I want this flux, okay, well that's that thing, well that's that thing, which is this thing, and then they proceed, blah, 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 and compute a bunch of stuff, and then they get, some answer, and then they realize, oops, whoopsie, I'm off by a minus sign, so let me just stick in over here, I will put in a minus sign. Now, it's, just for dramatic effect, I'm putting it only at the very, very end, and look what a ridiculous thing this is. This says that this value is equal to its own negative. Well, that's nonsense. It's just not true. Equal signs are statements. They are statements that matter, right? So, you can't say 6 equals negative 6. It's not okay. Does that make sense to everybody, I hope? Right? And again, if your focus is on whether or not you have the right numerical value in a box, the case could be made that, oh, yeah, well, who cares because the right numerical value is in the box. But again, that's not what this course is about. So make sure that all your reasoning makes sense. So where should you put it in? You should put in the minus sign at the point where the error first gets made. So it needs to go here, right? Because as previously discussed, ds and ndsdt are not the same thing when you've parameterized upside down. ds in this case is negative ndsdt. So you got to have that minus sign there. Everybody happy? Does that make sense? All right. Okay, so make sure to think it through. Okay, now let's talk about language a little bit. The surface we were just looking at was a paraboloid. And of course there's two orientations that we could put on a paraboloid. There's this one here where the unit normal vectors are, well, however you would describe that, but where those are the unit normal vectors. And then there's this other orientation where these are the unit normal vectors. And how am I going to distinguish the green ones from the blue ones? I guess I could write down the explicit formulas for them. That's a lot of trouble. In some sense, the whole purpose of language is that I not have to write down explicitly a formula for things I want to talk about. Right? So we want to have easy, convenient terminology to distinguish that green set of vectors from that light blue set of vectors. And, well, the language is not going to be perfect and precise. It just isn't. So that's not how we choose language with which to distinguish these two things. We choose the language based on what choices of words make it unambiguous which one I'm talking about. I know it's got to be one of these two. Right? So how would I describe these green vectors? Well, they all point at least somewhat upward. They don't point exactly upward, but they all point at least somewhat upward. None of them point even slightly downward. Whereas by contrast, these blue vectors all point at least somewhat downward. And none of them point even slightly upward. So the point is, these terms, upward and downward, unambiguously distinguish between these two possible cases, even if they're not perfect descriptions. Of course not. Right? But they remove all doubt as to which one you could possibly be talking about. Does that make sense to everybody? So the big mistake I want to warn y'all off of is some people will see this term here. They'll see upward, and then they'll instantly write down n equals 0, 0, 1. And very important to recognize that is wrong. That is complete nonsense. That is not at all what that means. When you have a surface described as oriented upward, it does not mean that this is your unit normal vector. It means that the third component's got to be positive. That's it. Right? No comment as to the other components. Everybody see what I'm talking about? Heads up on this, please. This is a very easy mistake to make. And I want to point out, of course, you don't even really quite need to know about this convention of language to realize that this is nonsense. Because this vector is not perpendicular to the surface everywhere. We know normal vectors have to be perpendicular to the surface. This isn't. This is obviously not right. Is everybody happy with that observation? Okay. All right. Now, sadly, the proper reasonable language to use depends a lot on the situation, and you've just got to think it through. Think carefully about what the what is the job at hand to find a word to execute, and then think through what the right words would be. Some people would say that these vectors here, for example, all point inward. And I don't really hate that. I that's why I put in, it's kind of okay. Tilde check mark there, because I don't think anyone would look at this word inward and think, oh, you mean the downward ones, right? It's just not. Nobody would think that. So I think this kind of does the job. This just is a little bit uncomfortable because inward suggests that there is an inside being bounded by the surface, which there is not for that surface. So I think inward is a suboptimal choice. I think much better in this case would be to describe it as upward. On the other hand, let's look at this surface here. Right? That sphere. And again, there's two orientations. There's whatever we're going to eventually call this one, and then there's whatever we will eventually call that one. These are our two possible orientations. And you know what? Inward and outward kind of crushes it, doesn't it? Inward unambiguously describes the blue one, and outward unambiguously describes the green one. So that's fantastic. Different surface, different appropriate language. You got to tailor your language to the circumstance. Does that make sense? Oh, and then just for comparison, what about this word upward? Which of these two orientations, light blue or green, which of these would be upward? Neither or both. This word upward does not do the job here, because the green orientation, some of those vectors are upward, some of them are not. Likewise for the blue orientation, some of the vectors are upward, some of them are not. This word here just does not do the job at all for that surface. Everybody with me? So you got to be careful, heads up, think through the geometry, figure out how to be unambiguous, optimally sort of unambiguous. Here's another example to think through. I'm going to let y'all take a look at that and think through the various different options and which ones, pros and cons. And how would you describe that orientation? Those two orientations. Okay. All right. Next. Don't put on the blinders, right? always head on a swivel, always looking for opportunities to make your life easier, because it comes up a lot. There is just y'all have heard me rave about symmetry theorems and how much effort I saved myself as an undergrad, paying attention for candidate opportunities to use symmetry arguments, and then doing it. Right, and it is much easier than cranking stuff out the hard way. So these are not symmetry arguments; these are different lucky coincidences, I'm calling them, but also really, really useful. So here we go. Let's look at this sphere described by rho equals 3. And let's see here. We want to compute the flux. And we've got a vector field given. Of course, the surface is given. So how do we compute this? Well, you could take this equation, think, hey, that's a spherical graph. Sweet. Spherical graph parameterization. You get a parameterization. It's got a lot of trig in it, but what are you going to do? That means a lot of trig would get into your vector field. You'd have to take your parameterization and do the partials and the cross product and find the capital impact. You're going to have trig everywhere. It's going to be a ton of inconvenience. It'll work out. It's doable, but it's a ton of inconvenience. Okay. So here's the alternative. Spheres centered at the origin have massive symmetries. We're not going to make an odd symmetry argument here. There is no such thing. We'll talk about symmetry arguments in a minute. But there's a different kind of symmetry that is really useful, and that is that the normal vectors to the surface of a sphere centered at the origin are always parallel to the position vector at that same point. And that's just a unique property of spheres. Gotta love it. That make sense? So, if I know that this normal vector is a multiple of the x vector, and I also know that its magnitude is 1, it's pretty easy to write down exactly what the formula is for that normal vector. That unit normal vector is that right there. Now, that's hardly any effort at all. And at that very, very low cost of thinking through that little bit of geometry, writing down the formula for this normal vector, I get to do a quick little test and see how convenient is it to do this integral on its own without using the parametrizing trick. And you just kind of look and see what you got here. Oh my gosh, look, check it out, this dot product 0. We're done here. We win. Game over. Almost effort free. That makes sense to everybody? You'd be surprised how often stuff like this happens in practice, and I'm not going to try to quantify it, but it happens surprisingly often. Yeah.
Why does the dot product mean 0?
Well, you can just literally crank out this dot product here. If you just multiply, you get xyz, and then minus 3xyz, and then plus 2xyz, and that adds up to 0. Yep.
If we had to do this in the exam, what evidence would we have to present to get credit?
Oh, just what I've got written here would be.
So you wouldn't have to
plenty.
Write out the dot product.
Oh yeah, no, I think it's perfectly. I think if you go from this line to this line, it would be an awfully persnickety grader that would feel like any more than that need to be shown. Yeah, it's pretty clear at that point. Yeah. Yep. Anybody else? Feel free. Okay, so, look, yes, there are algorithms in this class, and you do need to know how to, do the algorithms and how to take a deep breath and plow forward, and this is true. But, again, don't keep the blinders on and just always be plowing forward. Sit up and look around once in a while. Always be kind of looking for these opportunities. My own personal observation, when I see a sphere, especially a sphere centered at the origin, I'm thinking, this is an opportunity, right? Spheres are awesome. Spheres have fantastic symmetries. I got a lot of opportunity. So many good things that could happen, right? And before I get into parametrizing, I'm always thinking, okay, wait a minute, what could I do here? And I will just kind of instinctively think to make this argument, see what happens to the dot product. And, most of the time, no help. But 1 time out of 10, 1 time out of 20, boom. Well worth the effort. All right. Here's another example of, again, just, heads up. Don't just plow forward on everything. Just, look for convenient opportunities for awesomeness. Okay, so we've got a surface. It's sitting inside of this plane where y equals 3. Specifically, we're looking at the part of that plane that satisfies this inequality, which means we're looking at this kind of, 1950s era tube television screen shaped subset of that plane. And through that surface, I want to compute the flux of this vector field. Now, that's not hard to parameterize. You can see right here we have y as a function of x and z. You can use the graph parameterization, and you can take a deep breath and plow forward. You could. But here's the easy opportunity. Planes, also really nice. It's really easy to look at the equation of a plane and see what the normal vector is. Notice this says we're oriented in the positive y direction. The normal vector is obviously parallel to the y-axis. It's got to be this. There's my unit normal vector, my orientation unit normal vector. So I get to write that down immediately. Now, it's not clear how this dot product's going to work out and whether this is something that's going to be beneficial. I might still have to end up parameterizing, but let's play with this. Let's see where it goes. Right. The next observation to be made is that y equals 3 not only tells me what my normal vector is, it also tells me what I'm allowed to plug in for y in the vector field. After all, every point I'm interested, when I'm computing this flux, every point I'm interested in is on this plane. That means that for every value of the x position vector that I care about the vector field, y is always 3, which means that this second coordinate is just flat 0. And if that second coordinate is just flat 0, that's another nice little simplification that I get for my integral. How we doing? Everybody with me? So, okay, all right. So now, has this paid off enough? Are we going to have to parameterize, or can we make life good? And well, again, that dot product is 0. That means this integral is 0, and we're done. And we walk away. Everybody see what happened? Okay. So this was a weird one in the sense that there were a couple of things. Couple of geometric good fortune, if you want to say it, a couple of conveniences that presented themselves, and I had to notice both in order to be able to really fully capitalize. But if you make the key observations, then the question turns out to be very straightforward. Okay, so always on the lookout for that kind of thing. Okay, moving along. You may recall when we were talking about vector line integrals, I brought up this notation called coordinate line integrals. That was really kind of just an alternative notation for vector line integrals. It's really the same thing. It's just, written in terms of coordinates instead of thinking of the objects in play in terms of just, as vectors. We're going to do the same thing here. For very similar reasons, as it turns out. But anyway, before we get to the reasons, let's talk through the actuality of it all. What I have here is mostly old news. We have previously talked about n being this cross product, which I can write out in coordinates, which I can then compute by coordinates to get that. All of that business about capital N we've previously discussed. All I've done here is apply that to the ds vector, which is capital N times ds dt. So just effectively, I've just multiplied by ds dt, and all of this is effectively old news. I made the statement previously that it wasn't clear how this was going to be beneficial. It's also not clear geometrically. I mean, this is suspiciously suggestive of 2x2 change of variables. It's a real eyebrow raiser. I don't have time to go through and talk about why. There is actually some very natural, legitimate 2x2 change of variables in play. It's geometrically meaningful, and if I had the time, I would love to talk about it. We just don't have the time. You don't need to know that stuff, so I'm going to let that go. But if you're curious, come to office hours, catch me in some other context. I'll be very happy to walk you through it. It's about a 15-minute conversation. No big deal. But anyway, I'm just going to run with this as it is and point out that you can distribute the DSDT, and then you look at these coordinates, and it's pretty believable. Now, again, forgive me for the math crime here, but I'm going to pretend it's as if those cancel, right? They don't. But it's as if those cancel, and with that in mind, we would naturally want to call that dy dz. And likewise for the other coordinates. So, with that in mind, ds is that. We're going to use the usual convention of calling our vector field PQR, which is that. In other words, just plug in everything in terms of coordinates, and as a result, what you get is that this integral turns into, well, I'm going to say that, whatever this thing is, and this is what we're going to define as a coordinate surface integral. And it's a weird notation. It's particularly confusing because, wait a minute, our domain is a surface that's got like some angle to it. It's sitting up in space, and if it's sitting at an angle in space, what do you mean dx dy? This is not in the xy plane. So what does dx dy mean? Anyway, so it's pretty uncomfortable looking, but this is a common notation. Again, it's just an alternative to the notation we've been using that is my personal favorite for this context, at least. So if this notation here is clunkier and less geometrically intuitive, what's the point? Right? Why would we ever do this? Why am I even wasting your time with this seemingly purely less desirable notation? And two answers. One is cultural. I think it's a healthy thing to know what's going on sort of in the bigger picture, even if we don't actually go through and fully flesh all that out. And I've made the following statement before. I made the following statement when we were talking about coordinate line integrals, that there exist these things called differential forms. Very powerful. And frankly, in this context, when you're talking about surface integrals, this is what differential forms look like. Slightly different. There's some notation that we're leaving out here, but morally, this is what they look like. So this is a glimpse into some much more sophisticated, more powerful, very important ideas that we're just not going to be able to go further into. So I think that's kind of neat. It's worth knowing. And here's the thing. Because differential forms are so powerful and so useful, a lot of people really like this notation because they like differential forms. They're right to like differential forms. This is a very reasonable notation for a lot of reasons, again, beyond what we can do in Math 219. So, point being, though, you're going to see this notation outside of this course. No matter what I decide in Math 219, you're going to see this in higher level, physics and engineering courses. And so I need to make sure that when, not if, but when y'all see this notation, you need to know what to do with it. And so reminder, when you see this notation, remember that these differentials, these coordinate differentials, are just code for the ds vector. Right? You got to remember what order they go in. And by how they're paired, these P, Q, and R that you infer accordingly are just telling you what the vector field is. Right? So you can just literally take what's written in this form and reinterpret it as a vector surface integral of a vector field whose coordinates you can just see and write down. What do you think? Everybody happy with that? All right. Okay, let's talk about symmetry theorems. Again, y'all know I'm a big fan. I think they're wonderful, extreme time savers in a lot of cases. So here we go. We have a symmetry theorem for scalar surface integrals. I want you to notice how familiar the layout on the page of these statements is. I did that on purpose, very much on purpose. I want that analogy to be as clear as possible. So let's walk through the details. If you're computing a scalar surface integral, and if your integrand is odd, and if your color, yeah, I'll use yellow. If your domain is symmetric, and I emphasize, you got to have both, right? Both of these conditions have to hold. And if furthermore, I emphasize, you got to use the same plane for both of them, then your integral is 0. You're done. Walk away. It's awesome, right? You're big help. By the way, for whatever it's worth, somebody in office hours earlier today asked me about one of the assigned exercises, and I'm not going to say which one it was, partly because I've forgotten, but also partly because I want y'all to be on the lookout for it, right? I want you to, be heads up. One of the exercises, you can just make this argument right here. The integral is 0 by symmetry. It does not announce itself, right? And that's one of the things about symmetry. You do have to notice it for yourself. So anyway, be on the lookout for where to use this. And outside of this course, again, surprisingly often this kind of stuff comes up. Okay. All right. So we love symmetry. Good news. The bad news. Notice I underlined scalar surface integrals. This only works for scalar surface integrals. It does not work for vector surface integrals. For vector surface integrals, no luck. It just doesn't work. And you can kind of see, roughly speaking, why it doesn't work. Here's your vector surface integral. Here's a rewritten form of it. I'm going to use this rewritten form because I want to point specifically and distinctly to the normal vector versus the area itself, right? These two separate pieces. In particular, yeah, sure, these DS's, you could argue that if you chop it up in the convenient way, then this area over here and that area over there are the same, and you could kind of see maybe there's going to be a cancellation or something. But the problem is that you would also need these normal vectors to be the same. And they're just not, right? You can visually very clear these normal vectors they're just not the same. Right? The domain is symmetric here over this plane that I've drawn, but the normal vectors are different. And it's worse, it's not just that they're different, they're not even negatives of each other. They're just different. So we're kind of dead in the water here. Now I have to make a big deal out of this because, and I've made this observation too, as much as I love symmetry arguments, and y'all know I'm a big fan, right? They're dangerous. If you make a symmetry argument that actually doesn't work, right, then nothing you've written down is in any sense progress toward a solution. And that's the problem here, right? If you find yourself needing to compute a vector surface integral, and if you make an odd symmetry argument for a vector surface integral, nothing you've written down is at all, true and relevant to an actual solution. And it's just all wrong. There's nothing. As much as I want as much effort as I expend trying to give partial credit. It's my favorite thing when I'm grading is to give partial credit. I want to give partial credit. If you make an odd symmetry argument for a vector surface integral, none of it's right, not even close. It's just not right. And so there's nothing I can do. So it's a dangerous thing. So I hope this is enough emphasis for a vector surface integral, just like with vector line integrals. There is no odd symmetry theorem. So don't try to use one. Is that okay? That makes sense to everybody? All right. Quick side note, that there is a different theorem that is not worth talking about. There is a version of a symmetry. It's not odd symmetry. It's a different kind of symmetry. It's sufficiently awkward to define, awkward to work with, that it's just not worth the trouble. So I stop short of saying there is no symmetry theorem. Yes, there is a symmetry theorem. It's just not oddness, and it's much harder to work with. It's not worth your time. Don't worry about that symmetry theorem. It's just not worth the trouble. Okay. So, moving along. Okay, so y'all have heard me say the term differential forms a bunch of times. Again, I think it's good culture, right, to know that there are bigger ideas around in play that we're only going to see sort of glimpses of shadows of, right? But very valuable, I think, to know that they're there, to know that there are connections, even beyond this course, connections between the objects that we are talking about. So, neat to know, worthwhile to know, that both vector line integrals and vector surface integrals are fundamentally integrals of differential forms. So they really are kind of the same thing, different examples of fundamentally the same things. Now that's surprising, because if you think back to where did we define vector line integrals? Well, we were interested in work, a physical quantity called work, right? Where did we get surface integrals? Well, we were thinking about a physical quantity flux, and work and flux, right? The physical connection between those, seemingly none. Right? So I think it's a surprising fact that vector line integrals and vector surface integrals are mathematically fundamentally the same in so many ways. Very, very unexpected from the physics. Okay, so aside from the culture, the fact that these are both differential forms means that there are a lot of analogies. There's a lot of strong comparisons between vector line integrals and vector surface integrals. And I want to flesh those out because I think this is really, really useful in a lot of ways. So first of all, here's a parameterization of a curve. Got my curve here, and I can view position on this curve as a function of time. Apologies for the way I've drawn this, where the parameterization is kind of going downward and to the right. I just needed more space on the page, and this is purely a space-saving point, and I know it looks weird, and I'm sorry about that. Likewise, if I can get that to erase, here's a parameterization of a surface. And again, apologies for the, apologies for the sort of angled drawing. Again, I got to make it fit on the page. Okay. All right. So here's a bunch of participants, players in the vector surface integral game. And here are the players in the vector surface integral game. And here's a bunch of old news relationships between those various players, various objects. All right, so there's a bunch of different equations. Not immediately clear how they're related at all. Okay, but let's start pairing them up and noticing how unbelievably well they fit together. Okay, so here we go. Let's see here. Let's start with the velocity vector here. The velocity vector. You can see it right there and right there. The velocity vector comes from taking a derivative of my parameterization. Okay, now on to the discussion of surface integrals. The capital N normal vector. Now it's a different thing, but it does come from taking the derivatives, right? Plural, fine, you got to take a cross product also, but they come out of taking derivatives of the parameterization. So I say that the velocity vector and the capital N normal vector are kind of analogous in a way. And then etc. The unit tangent vector is the normalized version of that. You can see it right there in the equation. The unit normal vector, normalized version of capital N. You can see it in the equations right there. Notice the layout on the page. Analogous. Same layout. Same connection. Analogous connections, I'll say. And then you can keep going. Let's talk about the dx vector. The dx vector there, that which is equal to these, whose magnitude, blah, 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 plays exactly the same role as the ds vector, that which is equal to those whose magnitude here is equal to that other stuff. Again, notice this, it's the same layout in the equation, but they play analogous roles in these equations. Let's talk about the ds scalar. D little s scalar tells me the size of a piece of the curve. The d capital S scalar tells me the size of a piece of the surface. Again, the analogies are flawless. Everybody see what's going on there? Everybody see how this is? I mean, there's really strong analogies here, etc. Let's see here. Let me do the the pullback differential, dt. Right, the pullback differentials over here, dt ds. Just for the sake of analogy there. So perfect. Everything fits. So. What's this worth? Well, again, I think culturally this is it's just it's good to know that when things truly are really analogous to each other, it's good at least to be aware of that fact, right? And again, I think culturally it's good to know why, in some sense, that these are so analogous. It's because they're both the same thing. They are integrals of differential forms. Being as they are the same thing, it's really not that surprising that they lay out on the page so similarly. It's also useful, by the way, for learning purposes, sort of a pedagogical tool, and that is, let's see here. Let me zoom out so I can fit more on here. Now, I could go through here and continue the color highlighting. I'm going to be a little short on time, so I'm not going to do that. But if you were to extend the color highlighting down to here, it's a perfect correspondence. Everything still fits. Everything on the left corresponds to everything on the right. Being aware of these analogies gives you the opportunity then to take your existing understanding of one side of the page and use that to help you understand the other side of the page. So, for example, if you feel like you have some intuition or sense for what this is good for and where it comes from, well, this formula over here comes from similar things. It is good for similar things. It's not the same. Everything's different. This is two-dimensional, that's one-dimensional. This is related to work. This is related to flux. Vectors over here are parallel. Vectors over here are perpendicular, to the domain. So not exactly the same, but analogous. So you can, like I say, you can use your understanding of one side to help you understand the other side. The most specific examples, I think, of this are using your existing understanding of the dx vector to glean some additional understanding of the ds vector. And I'm going to confess, this D capital S vector is a tough concept to chew down. Right? This is a big bite of idea here. So think about the fact that it's playing the role kind of analogous to the dx vector as you're trying to sort that out in your mind. And then the other one is the capital N vector. It's really helpful to understand that its origins and its role very analogous to that of the velocity vector. Different, of course. It's perpendicular instead of tangent. Everything's a little different, but it plays an analogous role. It points in the direction of the parametrized orientation, and its magnitude is the stretching factor. There's so many analogies that it has in common. Okay, and we are out of time. We will draw the line right there, and see y'all on Friday. Hope you have a good rest of your day.